In this session, we will introduce the deep learning technology used in speech separation. Speech separation has been extensively studied in signal processing for decades. Depending on the number of sensors or microphones, one can categorize the separation methods into monaural, single microphone, and array-based multi-microphone. Two traditional approaches for monaural separation are speech enhancement and computational auditory scene analysis, CASA. Monaural methods analyze the general statistics of speech and noise and require a noise estimate. Multi-microphone methods make use of spatial filtering with a microphone array. Beamforming boosts the signal that arrives from a specific direction through proper array configuration, hence attenuating interference from other directions. Independent component analysis finds the demixing matrix from multiple mixtures of sound sources. CASA is based on perceptual principles of auditory scene analysis and explores grouping cues such as pitch and onset. A more recent approach treats speech separation as a supervised learning problem. The original formulation of supervised speech separation was inspired by the concept of time frequency TF masking in CASA. As a mean of separation, TF masking applies a two-dimensional mask weighting to the time frequency representation of a source mixture in order to separate the target. A major goal of CASA is the ideal binaural mask, IBM, which denotes whether the target signal dominates a TF unit in the time frequency representation of a mixed signal. Since the formulation of speech separation is classification, the data-driven approach has been extensively studied in the speech processing community. Over the last decade, supervised speech separation has substantially advanced the state-of-the-art performance by leveraging large training data and increasing computing resources. Supervised separation has especially benefited from the rapid rise in deep learning. The types of DNN for supervised speech separation include feed-forward multiplayer perceptrons, MLP, convolutional neural networks, CNN, recurrent neural networks, RNN, and long short-term memory, LSTM. Backpropagation is the standard training algorithm in deep learning. In supervised speech separation, defining a proper training target is important for learning and generalization. Different training targets lead to different mapping functions, from noisy features to separated speech. Different targets may have different levels of generalization. There are mainly two groups of training targets. That's to say, masking-based targets and mapping-based targets. Masking-based targets describe the time-frequency relationship of clean speech to background interference, while mapping-based targets correspond to the spectral representation of clean speech. There are a number of training targets proposed in the speech separation field. Well, the IBM, ideal binaural mask, is the first used in supervised separation. In the year 2014, Wang and his co-workers studied and evaluated a number of training targets using the same DNN with 3 hidden layers, each with 1024 units. The separated speech using various training targets is evaluated in terms of STOI and PSQ for predicted speech intelligibility and speech quality, respectively. From the results, we can see that among the 2 binaural masks, IBM estimation performs better in PSQ than TBM, target magnitude spectrum. In terms of objective intelligibility, the masking-based targets as a group outperform the mapping-based targets. In the scheme of DNN-based masking estimation, each frame of features is sent to a DNN to estimate the mask. Minor features include male frequency septural coefficient, MFCC, gamma tone frequency septural coefficients, GFCC, perceptual linear prediction, PLP, and relative spectral transform PLP, RASTA PLP. For supervised learning, features and learning machines are 2 key components. To our knowledge, deep learning was first introduced to speech separation by Wang and his co-workers in 2012. They used the DNN for subsband classification to estimate the IBM and reported strong separation results in all cases of DNN usage. In the year 2013, Wang introduced the DNN to address the speech separation problem in detail. This use of DNN for speech separation is illustrated in the figure. The input signal is passed through a 64-channel gamma tone filter bank to derive subband signals, from which acoustic features are extracted within each TF unit. These features from the input to subband DNN, 64 in total, to learn more discriminative features. After DNN training, input features and learned features of the last hidden layers are concatenated and fed to linear SVM to estimate the subband IBM efficiently. The above algorithm was further extended to a 2-stage DNN, where the first stage is trained to estimate the subsband IBM as error, and the second stage explicitly incorporates the TF context in the following way. After the first stage DNN is trained, a unit-level output before binarization can be interpreted as the posterior probability that speech dominates the TF unit. Hence, the first stage DNN output is considered a posterior mask. In the second stage, a TF unit takes as input a local window of the posterior mask centered at the unit. In the year 2014, Xu and his co-workers published a study using a DNN with RBM, pre-training to map from the log power spectrum of noisy speech to that of clean speech. More input frames and training data improve separation results. Up to now, many subsequent studies have since been published along the lines of TF masking and spectral mapping. After deep learning was demonstrated to be capable of speech enhancement, DNN has been successfully applied to speaker separation under a similar framework. Huang and his co-workers were the first to introduce DNN for this task. In the year 2014 and 2015, they proposed the two-speaker separation method based on DNN, as well as RNN, recurrent neural network. The aim was to map from an input mixture to two separated speech signals. The method used the TF masking, binaural or ratio, to constrain target signals. DNN and RNN perform at about the same level. Talker-dependent means the same two talkers are used in training and testing, while interfering talkers are allowed to change. Talker-independent separation can be treated as unsupervised clustering. In the year 2016, deep clustering is the first approach to talker-independent separation by combining DNN-based supervised feature learning and spectral clustering. In 2017, recognizing that talker-dependent separation ties each DNN output to a specific speaker permutation variant, PIT seeks to anti-DNN outputs from speakers in order to achieve talker independence. In the year 2018, Liu and Wang proposed the CSA-based approach by leveraging PIT and deep clustering. Speech separation can be classified into monaural separation and multi-channel separation. Monaural separation, also called single-channel separation, contains speech non-speech separation, speaker separation, and separation of reverberant speech. Multi-channel separation, also called array separation, has some research on special feature-based separation and masking-based beamforming. The use of special information afforded by an array as features in deep learning is a straightforward extension of the earlier use of DNN in monaural separation. One simply substitutes special features for monaural features. Since traditional beamforming with an array also produces a monaural output corresponding to the target source, TF masking based on special features may be considered beamforming, or more accurately, nonlinear beamforming, as opposed to traditional beamforming, that is linear. Recently, Zhang and Wang developed a DNN for our IRM estimation with a more sophisticated set of special and spectral features. DNN-based separation over a short few years has greatly elevated the state-of-the-art for a wide range of speech separation tasks, including monaural speech enhancement, speech deliberation, speaker separation, as well as array speech separation. That's all for our lessons. Thank you.